Hello everyone, my name is Hannes. I'm VP for Product for our 3D simulation environments at Blackshark.ai. Welcome to my talk and thanks for joining. I will present you our AI-based custom feature detection solution, which can be facilitated for a procedural 3D twin of Earth. This is exactly what we did a couple of years ago already for the Microsoft Flight Simulator. So AI-based feature extraction to build this digital twin. Back then when we started, AI technology was at a completely different stage. So we had to build our own capabilities, our platform, our tools. And Blackshark's vision was never to provide a 3D digital twin for incredible gaming experiences only, but to provide this groundbreaking technology to other industries for national security, to professional flight simulation, and beyond. Meanwhile, AI has taken the world by storm, and we productized these capabilities so that you can leverage them as well and use them, as we do in-house. But I want to show you today how you can use those things to generate your custom 3D twin of Earth, streamlined for your use cases and your applications. We want to support you and enable you to be as fast, efficient, and as flexible in your 3D terrain and custom 3D twin creation process. And this will be the core of my presentation, how this fits into your needs and what's possible based on it. First, I want to elaborate a little bit why a procedural 3D twin is necessary. On the example of Oahu Island on Hawaii. This is a screenshot of Oahu taken from Google Earth. And there are several other technologies available to create a 3D digital twin, like photogrammetry, as it's mainly used in this case, or reality capture. And all those technologies are awesome and really great for the right need. And meanwhile, also Gaussian splatting and NERV are very interesting technologies for certain use cases. Especially if it's to provide a realistic representation for the human eye and brain. Those technologies like photogrammetry and reality capture are just perfect. And even for professional flight simulation use cases, or some of the professional flight simulation use cases, these textured 3D meshes provide a very good spatial context and are just fine. But for some simulation use cases, our 3D digital twin is used for, and the reason is these meshes are missing one essential ingredient, and this is the semantic metadata. That means that we can provide the context of the type of object and the material for every pixel at any time. And this contextualized data makes our 3D digital twin machine readable. So it can be used for autonomous sensor-based system training. I'm gonna tell you something about the use cases first. So I mentioned professional flight simulation as one application already. Herm Bessar yesterday from CAE mentioned that they're using Blackshark for that as well, because we are so performant and realistic. And what you see here is the new True Varies simulator by True Simulation. It's a VR-based simulator, and the image generator is based on Blackshark's globe and airports as well. Then we have customers for hardware in the loop, sensor in the loop, and sensor simulation use cases. Here the main reason is, again, the realism, the performance, the semantic data, but also that we can easily permutate this procedurally generated globe. So if we want to change the appearance or the position of any feature on this procedurally generated globe, it's just a matter of changing one parameter, basically. Sensor simulation in general is one typical use case. For instance, for night vision goggle simulation, infrared sensor, radar simulation, and so on. Another interesting use case is synthetic training data generation. So we can procedurally place objects of interest based on the terrain semantics and permutate these scenarios in very large amounts so that our customers can use this synthetic training data to train their object detection models. Very large-scale geospatial simulation in general. This is again interesting because our Globe SDK is so performant that we can simulate very large theaters with thousands of entities in real time. And geospatial visualization in general. But here we need to be careful because we create a geo-representative globe, meaning the footprints of the buildings are correct and on the right spot, but the facades are procedurally generated and are not representing the reality for now, let's say. This is our hometown, where we are headquartered in Graz, Austria. And this is Graz during January. So we can simulate all kinds of features and parameters like time of day, weather condition, which is important for all of these use cases as well. We don't do the weather simulation ourselves. Here we support standard Unreal Engine plugins like Ultra Dynamic Sky. But of course, it works with any other weather plugin as well. But let's go back to Oahu. This is our version of Oahu, procedurally generated, looks pretty neat, has all the semantic features, and is generated based on 50 centimeter satellite data, plus so-called AMDP data, so airport vector database information, which is provided by one of our data partners. And the satellite data in combination with this vectorized database enables us to auto-generate the entire globe and all the airports on the globe in this fully automated manner, ready for all those use cases. But if we go further away from the airport and we don't have vectorized information anymore, then we don't have enough details to make it good enough for ground-level simulation. And of course, we want to have a high-detailed 3D digital twin that can not only be used for flight simulation and higher altitudes, but also for ground simulation, so that it can be used for multi-domain applications and use cases. We want to have that, use it, and play it, simulate it on an as accurate and realistic 3D twin. And that's where our Orca Hunter tool for ML-based feature extraction comes into play. Because with that, you can train your own model and extract exactly the features you need for your use case. And the goal, of course, is then to use this semantic information in combination with procedural content generation, like PCG from Blackshark and PCG or Megascans from Epic to generate this realistic, real-time simulation-ready 3D twin. So, how is the workflow? First, we need sensor input data. Blackshark has one global data set with a 50 centimeter resolution, and we use digital elevation model alongside with it. And we have pre-trained models to extract the features everyone needs and wants. We can containerize those models and parallelize these models. So if necessary, we can run hundreds or even thousands of GPU nodes at the same time and provide a close to real-time feature extraction pipeline based on this. This creates a georeferenced database, and this is used then in our Synth3D product line, our Globe plugin for Unreal, and in combination with PCG, it creates this photorealistic 3D twin. And with the Unreal Engine plus these features, which can be extracted with HUNTR, you can basically create a very, very detailed 3D twin. So we consider our Synth3D globe as a base globe, and in addition with HUNTR and with PCG and Megascans, you can hone it to a very accurate and detailed level. In terms of scalability and speed, let me show you this one slide here. So it's a case study about building footprint and building vector extraction for 12,000 square kilometer. The classic approach of this customer was to take multiple shots, capture multiple shots, and create this 3D map in a traditional way with existing tools. And this took the customer in average about 8 weeks to provide an update for this 12,000 square kilometer. With our Orca Pod container for building footprint and building height extraction, based on 50 centimeter satellite data, it took the customer less than 5 hours with an awesome accuracy. This is just one example how powerful these machine learning models in a containerized way are. So we have machine learning models for 50 centimeter satellite data pre-trained. Here's a visualization of the results. We have other models based on 7.5 centimeter aerial imagery as well, which of course provides a much better accuracy and resolution from the output side as well. We have a pre-trained road network model. This is especially interesting for regions where no other road vectors or no OpenStreetMap data is available, or where you need high update rates based on satellite data. And we also have a land use, land cover model in a containerized way, so we can flexibly extract a base model of the features for the terrain. Let's go back to our how again. Because something is not right here. It doesn't look like Hawaii, right? And like Oahu. There's one thing missing. I think the palms, they are very important. The palm trees, they make the appearance. And now we're gonna use additional custom sensor data. It can be aerial imagery, drone-borne imagery, nadir, oblique data, multispectral, hyperspectral. Basically, you could take your iPhone image as input into Orca Hunter and train your custom machine learning model, which is, after the training, containerized and can be run at large scale. This is how the Orca interface looks like. It's a live labeling tool that allows you to label the objects directly on the image and get instant feedback, making it very easy to see how the model is learning in real time. It's a no-code experience, so users don't need to code a single line It's really you log in, as you will see, and you can start to train. The interface, or the interactive interface of the platform, provides an intuitive interface that allows you to visualize, detect the results, to export them as raster, as segmentation mask, to filter them, and so on. And this provides you real-time insights, which can then be used for the visualization of the high-detail 3D twin of the globe. As I mentioned, it's completely sensor independent, so you can use any sensor data in a raster format. You simply upload it and you get going. So I prepared a screencast. And now we're going to do our palm tree detector for Oahu. It's, of course, pretty difficult to extract or to detect palm trees from 50 centimeter satellite data. Therefore, I uploaded higher resolution imagery. So I'm using here 15 centimeter aerial imagery. As you've seen, I simply logged into the platform. We use our browser as interface, but it can be deployed on-prem on a local GPU node on your laptop. The standard version runs on AWS. So if you get access, you can basically start to upload your data and to train it. I'm creating a new AI model here for 15 centimeter data. You can provide up to 10 different image layers. So RGB would be 3. Near infrared is often used, but you can use hyperspectral or multispectral imagery up to 10 layers as well. And now let's have a look where the palm trees are on Oahu. Here we go. I define a labeling area. And I try to get as many palm trees within this labeling area and start labeling. We have brush tools, polygon tools, rectangle tools, and so on. So it's a very, very intuitive interface. In this case, in the standard version on AWS, we don't have a hot GPU available at all time. Therefore, I'm starting the GPU on the server in the background. But I can already start to train and label the data. But of course, if you have an Orca Hunter version with a hot GPU, it would directly start to train. In this case, I'm doing a palm tree detector, but of course, it can be anything. Whatever can be distinct by the human eye and human brain can be trained in this manner with Orca Hunter. And yeah, it's really interesting to see how the model learns then and how this interacts with your own brain basically as well, because if no, you got it right or wrong, and you just provide some additional feedback and input. I didn't provide any negative labels, so everything yellow is palm trees. As you see, you don't need to train it accurately, pixel accurate or so. You simply say, this is what I'm interested in. Basically, you can just put a dot on it and say, that's the feature or the object or biome or whatever I'm interested in. And the model starts to train. And now you see on the right-hand side how the model provides visual feedback. So the GPU is up now and is running in the background and processes all the input data in a phasing manner. So sometimes it's overshooting, and so it's getting better and better. Sometimes you do then a label and you think, you overreacted, but in the next second, the model got it right already as well. So you saw, this took us maybe 5 to 10 minutes now, and you will see, or you see on the right-hand side, the results of this model already. And of course, with each additional training area and each additional data set you provide, and so on, the model gets more robust, more accurate, as you can imagine. So I sped this up a bit so that we can see the inference runtime as well. Okay, pretty good. Okay, I think that's the number, the fourth or fifth labeling area I created here. And the model is doing pretty good already. In some cases, of course, the model is picking up the shadows of the palm trees, which we want to avoid. So we provide a negative label, as you can see here, to make it clear to the model, I'm looking really for the palm trees and not the shadows. And you can watch the model on the right-hand side, how it gets trained. Okay, pretty good. Missed one here. Up on the interface, you see the number, so 1 for negative and 2 for palm trees. So basically, I have my fingers on the keyboard and I can super quickly jump between each feature so that I can label as efficiently as possible. So we finished the training now, meaning we are happy with the results and with the accuracy. Otherwise, we could keep on going and provide additional input data and labels, of course, but let's start a detection run now. You can either select a certain area where you want to detect the features, or you can run it for the entire area you have here in the interface, or you can do batch processing as well, meaning you can say, okay, the whole country in a containerized way if you want. But here we are good with a small sample. I just want to show you the workflow, how easy it is to do a custom palm tree detector and pass this on to our SDK to use it then for procedural content generation. So you see here the inference is running based on one GPU node, but that's exactly one thing that could be parallelized with several GPUs. So we have customers running it on a local GPU cluster on 4 GPUs, which provides then pretty good performance in the extraction as well. Let's fast forward a little bit. Okay, this is interesting here. So you see already, so while the inference is running, I can zoom in and see if the results are good enough. If I'm not happy, then I would stop the inference basically and do a little bit more of retraining. But we are good here. But on the right-hand side, you see that you can then download the segmentation mask or the vectors. The probability, the entropy are available as well. So if you are into machine learning, okay, 94%, almost done. The water body down there, I cleaned up after the detection process. And now let's have a look on the results. So those are the geolocations of the palm trees now. And I export these geolocations as geopackages as well. Yeah, that's going on now. And the segmentation mask so that I can use it in our Globe SDK for the 3D twin generation. Okay. And now we have the geolocations in the Globe SDK and our Unreal plugin. And for the locations I detected, I placed U assets, so palm trees as U assets, as you can see here. And now we're going to compare the results with the satellite data that is underneath. So, okay, we missed this one here, for instance. But apart from that, okay. There's one example then. Of course, we didn't detect where the actual tree is growing, but the leaves or the position of the leaves. And of course, this can be combined with several layers at the same time. So if you want to detect other features at the same time for the same region, you could train up to 16 classes at the same time. That's an interesting one. But could be filtered out easily, of course. So if I say don't place palm trees within building footprints, this would be gone immediately. Okay. And yeah, the model took me half an hour maybe, all in all. As I said, Orca Hunter is a very generic training and labeling tool. So this morning I did this model with it. Just to show you, it's not about geospatial data only. You can do a pizza detector as well, and I separated different classes here. This took me, I think, 5 minutes. So I just downloaded some pizza images from the internet, provided some labels, and on the right-hand side you see the results. But in this context, for the 3D twin creation, of course, it's about geospatial data. So we have the 50 centimeter base globe. We saw the 15 centimeter based results, but for high detailed road reconstruction, maybe we want to go even higher. We have a data partner that provides us with 2 centimeter imagery, so aerial imagery. And in this case, I did a model to extract the geolocations of traffic lights. At the beginning, I wanted to do, I think, signposts, traffic lights, and the lanes, so the markings of the road at the same time. But it turned out that the posts were a bit tricky, but for the traffic light, it worked very, very good based on the 2 centimeter imagery. So, of course, you need to try it out a little bit and test what works and what doesn't work. But the process is always the same. You extract the necessary features, you get the geolocations and the segmentation masks, and you can use that then for PGG and PCG-based content creation. And of course, the more time you spend on it, the more robust the model gets. It has to do with, metadata, what's the shadow length. So the more diverse input data you provide, the more robust the model gets. So if you jump to a completely different geolocation where things look different, of course, you can use that as well, and can really come up with a global model if you provide the right amount of data and labels, of course. So we have the input data, we have the features extracted for our need, and now if we combine that with, in the future, FAB, or all the textures, all the procedural mechanisms within Unreal Engine, like PCG, we can create and recreate, in this case, roads, including road clutter, if we extracted the position of of those traffic cones in a very, very accurate way. So in this 2 centimeter imagery, of course, the traffic cone could be perfectly well spotted. We can extract the geolocation, and we can combine this with the asset library and the procedural generation for instance, those lane borders. This is basically what we do for our airport generator as well. So we extract features where we don't get this provided by our data partner, which makes us very, very efficient in the airport generation and creation process. Back to Oahu, 50 centimeter PCG-based buildings extracted from the satellite data, synthesized terrain texture based on land use, land cover information we extracted. And currently, we are heavily working on a ground level based auto generation pipeline as well, as you can see here. And so far, we only had examples where we had a top-down view, so nadir imagery, meaning we only saw the rooftop, but we didn't see any facade information, and therefore our facades are completely made up by our artificial intelligence. And the next step is, of course, to combine the facade information for each building based on our procedural content generation pipeline. And just to give an idea, so here again, I spent half an hour in doing a window detection pipeline. Meaning if we know that this shot was taken from a certain angle and altitude, then we can align and we can count the number of windows for a certain facade of the building to meet reality as close as possible. So we have now for this building, for instance, the segmentation mask. We can, here in this case, we could separate them possibly. So this is of course then after processing where we vectorize those positions and so on and use this position and this vectorized information for this specific building footprint. Currently, the facade would be completely made up. In the next version, we can then combine these features we extracted from oblique imagery and pass it on to our procedural content generation pipeline. Currently, we randomly generate those buildings based on all kinds of input parameter to make it as geo specific as possible, so geo-representative. But the more input data and the more features we get from HUNTR and our Orca Pod containers, the better we can meet reality in a simulation-ready, high-performant 3D manner. Unreal Engine helps us a lot. In this case, the next thing we're gonna release in our next version are BBR-based streetlights. Just to give you an idea, we're also gonna release on-the-fly collision at global scale. And you see how we go closer and closer to meet reality and meet a simulation-ready 3D digital twin. Yeah. Okay. That's it from my side already. I'm happy to take your questions and to have some follow-up discussions. My colleague Rick is here as well. He's based in the US, Florida, our director for 3D simulation environments. And yeah, thanks for your attention. I hope you enjoyed it. It was interesting to you. And yeah, let's discuss how we can drive this forward together. Thank you.